last couple of talks. Let's welcome Debmalya.
Thanks, Rasmus. Thanks to all the organizers for inviting me to give this talk. And thanks to all of you for sticking around till the end. So I'm going to be talking about this general area of algorithms for network unreliability. I structured the talk mostly as a survey. So I'll talk a lot about sort of the general area and what's known and what's not known, hoping to get you excited to, maybe some of you at least, to work in this area. But towards the end of the talk, maybe in the last third of the talk, I'm going to be talking about a specific result. If I can get this to work. Okay, so I'm going to be talking about a specific result in the last part of the talk. And that result is with Ruoxu Cen, who is my PhD student, and he is here. He has been here for the entire semester. Hope some of you got to interact with him. William Hay, who was my undergrad student and now is a PhD student at CMU. And Jason Lee, who many of you know, he was is a postdoc at the Simons Institute, is going to be starting as an assistant professor at CMU in a few months. All right, so what are we going to be talking about? What is this thing called network unreliability or network reliability? And it really is about asking this very basic question. So what's the role of a network in general, no matter what the application is? The role of a network is to connect, right? It connects individuals, it connects entities, it connects networks. So it's very natural for us to ask, how robust are those connections, whatever we manage to connect using the network, how robust are they to edge failures? Because all networks, no matter what the application is, suffer from failures from time to time. And this general question applies to a broad range of applications. It's really application agnostic. So whether you are looking at a network for a circuit on a chip, or a communication network, or a road network, or any other kind of network, this question broadly makes a lot of sense. Now, in this particular talk, I'm going to restrict myself to just undirected networks. Of course, the broad question also makes sense to directed networks, but for the purpose of this talk, I'm going to be only focusing on undirected networks. Now, in order to make this question concrete and sort of get specific problems out of it, I need to tell you what I mean by robustness, what kind of properties am I looking at in the network. And I also need to tell you what is my model of edge failures, how do they fail. Okay. So in terms of defining robustness, there's really a very broad range of problems that people study. I'm not going to go through all of this list right now, but in a couple of minutes, I'll come back to this list. So there's a lot of different connectivity properties that you might want to preserve in your network under edge failures. But what kind of edge failures are we talking about? Traditionally, we always focus on worst case failures. Okay, so we want to say what's the fewest edge failures in a worst case sense, adversarially chosen edges, that are required to disrupt whatever property, connectivity, robustness property I have in my network. Okay. So let's take an example. So let's take the first robustness property. It says that a graph, i.e. all the vertices of the graph, remains connected. Okay. That is a very basic property I might want of my network. And I want that property to be preserved under edge failures. So if I look at the global min-cut problem, what that's asking is, what's the minimum number of worst case failures that will disrupt that property? What's the minimum number of edges that I need to take out in a worst case sense until the network gets disconnected? Similarly, you can look at the second property. So it says, okay, so maybe what I really care about is not the entire network staying connected, but a particular pair of vertices S and T staying connected. That's what I care about in my application. And then again, you could ask, what's the minimum number of edges, again chosen adversarially in a worst case way, that when removed, when they fail, S and T, that particular pair gets disconnected. Okay, and that's the minimum ST cut problem. So in this way, most of the problems that we study in graph connectivity can be modeled in this manner, where there's some property that you want in your network, and you're asking, okay, so what's the worst case failure? What's the minimum number of failures of edges chosen in a worst case way that will disrupt my property? And that's what I want to figure out. Okay, so that's what's been studied a lot over the last 50 years. What I want to talk about today is a little different in terms of the failure model. And the difference is this. So instead of asking about what happens to a network if there's a worst case set of edge failures, what I want to talk about is what happens to a network when there's a random set of edge failures. Okay, so I'm no longer asking for a worst case minimum number of failures that disconnects my network. I'm saying, let's say every edge fails in some random way. Now, is my network connected or not? Okay, and how do I distinguish between a robust network from a non-robust one? So let's take this and make this a little more concrete so that we can argue about things. And in fact, even before I give you the concrete definition, let me say a little bit about why do I care, right? Why do we care about random edge failures? Now, one very natural reason for caring about random edge failures is that in many applications, in many situations in practice, that's sort of a better model for how a network fails, right? So if you think of a road network, it's not that some adversary is coming and clogging up some roads. What's really happening is certain roads with some probability fail. Now, of course, we can keep arguing about what the precise random model is and what kind of dependence you have and things like this. But at least it seems a reasonable model to study. It's also the case that a lot of different fields have converged to this and so there are all these different books which talk about both models as well as properties of graphs under random failures. So it's a very well studied topic in an empirical, practical sense. But if you look at algorithms, there's hardly anything known. So we know very little about algorithmic results for what happens to a network under random failures. This is distinct from saying something about combinatorial extremal results. So in an extremal sense, we have, of course, there's a lot of study of random graphs. So we know something about what happens in random graphs, but you'll soon see what I mean by the lack of algorithmic results. Yeah, and that's at least one motivation for why I want to study it. Okay, so now let's make this concrete. So I've been sort of waving my hands and giving you some general ideas of what I want to talk about, but let's now make this a concrete set of problems. So I have some input graph. Okay, this is some arbitrary graph on n vertices and m edges. And my failure model is the following. Every edge in the graph fails independently and identically with the same probability p. Okay. Now you could argue that in many situations, it's more reasonable to say that different edges fail with different probabilities. It turns out it's not very different from, so it turns out that you can actually simulate those situations using this uniform model, at least unless there are like very extreme parameter values. So let's not go into that. Let's stick to this very simple uniform model. So I have a graph, every edge fails with some probability p. What I get out of this process is some random graph g of p, and I want to argue about this graph. I want to understand how robust this graph is. In particular, the algorithmic question, given the graph and given the value of p, is the following. I just want to estimate the probability that this random graph, g of p, is robust in whatever sense of robustness I want to study. Okay? And again, there's all these different definitions of robustness, as I said, that we might be interested in. So we might be interested in, okay, so this random graph g of p, is it connected? Or this random graph g of p, does it connect a particular pair of vertices s and t, or various other things? Now, in order to keep things focused, and also because there's very little known in this area, I'm going to really focus on just these first two problems. Okay, so let me write those problems a little more clearly. So one problem I'm going to talk about is the single pair network unreliability problem. So this problem asks the following. I give you a graph. Every edge fails with probability P. Find me the probability that S and T, a particular pair of vertices in my graph, are connected. So that's problem one. Problem two, which is going to be the bulk of my talk today, is very similar, except that I don't give you a particular pair of vertices S and T. I give you the graph, I give you this value P, and I ask you what is the probability that the graph G of P, after edges are failed with probability P, is connected or disconnected. Okay, I mean, of course, these two are related, whether it's connected or disconnected. So is this problem space clear? Any questions about the sort of general definitions of problems that we are going to talk about? Okay, good. So that's our problem. And here's a very sort of sequence of works in the late 70s, early 80s that established the following eventually. So it says that both of these problems, the single pair and the all-terminal network unreliability or reliability problems, these problems are all of these problems are Sharpe hard. Okay, in fact, Sharpe complete. So really, we don't expect that we can precisely, exactly compute these probabilities. And in fact, this last paper, the paper due to Provan and Ball, that said something more. It said that it's not only Sharpe complete to find these exact probabilities, but it's also Sharpe complete to find approximate probabilities where the approximation factors are some parameter epsilon. The only catch is that they allowed in their reductions, they allowed epsilon to depend on the size of the network. So in particular, epsilon was exponentially small in the size of the input graph. Yeah, so that's a result they got. And in their conclusions, they write that we should note that a seemingly more difficult unsolved problem involves the case where epsilon is constant, i.e. it is allowed to vary, it is not allowed to vary as part of the input. So that was the sort of very early phase of work in this area. And that established this problem, the problem where you want to find the approximate the value of reliability or unreliability up to a constant, let's say up to a factor of 1.1 efficiently. That problem was left open by this early work. All right.
Sorry.
Yeah.
I'm worried.
Yeah.
Question. What about sort of intuitively, I think I know of some applied people who would prefer epsilon to be a small polynomial.
Yes. So we'll get to that soon. Yeah.
Okay.
Yeah. So we'll get to algorithms that can handle that case. All right. So and that's where the story sort of ends with the single pair network unreliability problem. Okay, so till now we haven't resolved this question. So if I even gave you epsilon to be a constant, there is no efficient algorithm that can find, let's say, 1.1 approximation to that single pair network unreliability.
And this was supposed to reliability and unreliability.
It applies both to reliability and unreliability. Yes.
Sorry, and is this an additive or a multiplicative approximation?
Let's say multiplicative. Let's say even a fixed constant, 1.1 approximation. Okay. I mean, this particular result, the epsilon was additive, but the one that's like wide open is, can I get a 1.1 approximation? Michael, you had a question?
I'm just this can only be true if the actual probabilities are exponentially small.
So yes, we are going to, sure. We are going to talk about it. You're right. Yes. Okay. Any other questions? Okay. So the rest of my talk is going to be about the all-terminal network reliability, unreliability, or reliability problem. So this is basically the problem where, again, I give you a graph, and every edge fails with some probability p. You can even think of p as half. It doesn't really matter. and I want you to figure out what is the probability that the graph gets disconnected, or what's the probability that the graph stays connected. And of course, these two are the same if we are talking about exact numbers, but if we are approximating things like that. Okay, so these are the two parameters we are interested in, reliability and unreliability. I'll call them R and U respectively. And as I said, these are equivalent in terms of exact computation. U is just 1 minus R. But if we are looking at multiplicative approximations, which is what we are going to do today, then these are different problems. In fact, I'm going to focus on one of them, and I'll briefly say what's known for the other one. And the techniques that go into the two are very, very different. So at this point, the next phase of research in this tried focusing on special cases of these problems. So Karp and Luby in 1985, they gave an algorithm that estimates or approximates the unreliability parameter, but only applies to planar graphs and in a model where the expected number of edges that fail is not very large. It's like order log n. Okay, so it's a very sort of specific result about a particular class of graphs. And then about 10 years later, Alon, Fries, and Welsh, they studied the reliability problem. So you want to approximate reliability, but they studied it only in dense graphs where the minimum degree of every vertex is n, and again gave an approximation algorithm for that case. Okay. Now I should mention that this last result is sort of a corollary of something broader. Like they looked at a broader class of dense instances of problems, and this just falls out as a corollary. So the first general purpose algorithm for this problem, and I'm calling the first generation of algorithms for the problem. We'll see there are subsequent generations, of course. That's why I'm calling it the first. But the first algorithm that gave, without any conditions on the input, it gave a fully polynomial time randomized approximation scheme for estimating the unreliability of the graph. It doesn't work for reliability, only for unreliability. And that was due to Karger in 1995. So let's just go over exactly what this algorithm does. So you give it an epsilon. It will give you a 1 plus epsilon approximation of the value of unreliability. So how unreliable the graph is, what's the probability it will disconnect. It will do that in time that's polynomial in n and epsilon. It's a fully polynomial time approximation scheme. So that addresses Rasmus's question. Even if epsilon is inversely polynomial in n, this algorithm still remains polynomial time. It is a Monte Carlo algorithm, so there will be some small chance that the algorithm will fail and give you some junk, but that probability is going to be 1 over polynomial in n. And the algorithm runs in time something like m times n to the 4. Okay, so at that point of time, the first algorithm, the goal was to just get a polynomial algorithm. It wasn't so much to optimize the running time. And then about almost 20 years later, Harris and Srinivasan, who basically took the same algorithm with some mild modifications, but did a much better analysis of the algorithm. They showed that indeed the running time of the algorithm is about n cubed. So the previous results says the running time could be something like n to the 6. This drastically reduces it to a little over n cubed. Any questions about just the statements? Yeah.
Epsilon strangely does not appear in the runtime. Am I missing something?
Yeah. So there are poly 1 over epsilon terms which I'm suppressing. Okay. So I'm thinking of epsilon as 0.1. Other questions?
Also, this better analysis doesn't depend on the edge. This n cubed, what's dependence on the edges, where it's not depending on that at all?
It's not, because the number of edges is, I'm assuming, is bounded by polynomial, bounded by n cubed. If the number of edges is very large, then as in you have a lot of parallel edges, for instance,
okay,
then there will be some linear terms dependent on that. Sure. Okay, but let's assume for now that the number of edges is n squared. Any other questions? Okay. So what's going on? So what's the main idea here? So here's maybe a very simple but key observation. So the observation is just this. So when does a graph disconnect? So I'm randomly failing edges with probability p. If the graph has to get disconnected as a result of this process, it must be the case that all edges of some cut must fail, right? If in every cut at least one edge survives, a connected graph will remain connected. That's just a basic simple fact. But now that you have explicitly stated this, you can use this to think of this problem in terms of Boolean formulas in the following way. So what you do is you define a Boolean variable, let's say x sub I. That's an indicator variable for whether the edge e sub I fails. So x sub I is 1 with probability p, and 1 minus p with probability, and 0 with probability 1 minus p. And all the x sub i's are independent. Every edge is failing independently. Okay, so you define this Boolean formula, Boolean variable. So now we can say that the disconnection of the graph, of the random graph, corresponds to the following DNF formula. So this DNF formula takes each cut in the graph and represents the cut in terms of a conjunction. So you take the first cut, you enumerate all the cuts in whatever order you want, take your first cut, look at all the edges of the cut, and write a Boolean formula that's the conjunction of the variables for all those edges. So note that if the edge fails, then all these variables are set to 1. So any term in this Boolean in this formula evaluates to 1 if the corresponding cut fails. Now, as we argued on the first line, the entire graph gets disconnected if some cut fails in the graph. Of course, multiple cuts can fail, but at least one needs to. So the failure of the disconnection of the graph corresponds to this Boolean formula evaluating to true. Right? This is an exact correspondence. So determining UGP, the unreliability, becomes a question of figuring out the probability that this Boolean formula evaluates to true when we set every variable to true with probability p independently. Okay, that's the basic equivalence. So here's an example. So I have like 4 edges here. Let's look at just one cut. Let's say the cut that contains the edges E1, E2, and E3. That's a cut in the graph. So I've written this term x1 and x2 and x3. So if all of those variables are 1, then this cut on top, this cut will fail. Okay, and you write this for every cut in the graph. Great. So I have this. So what do I do with this? So I now need to evaluate the probability that this formula is true. And here's a beautiful theorem. Maybe some of you have already seen it. This is a classic result. So this is due to Karp, Luby, and Madras. And it says that give me any Boolean formula. I don't care what the formula looks like. There is a fully polynomial time approximation scheme for estimating the probability that this formula will evaluate to true when every variable is set to true with probability p. Okay? So exactly what we want. If you give me a Boolean formula, give me a probability for each variable evaluating to true. This algorithm says I can get you an approximation of the entire probability formula being true. Okay. So it seems like what I should be doing is writing this formula out, the one that I wrote on the previous slide. I'm calling that the cut formula, and then just apply this result. What's the catch? Yeah, it's too big. Formula is just too big because I have an exponential number of cuts in my graph. And so I can do this, but how do I deal with the fact that I have too many cuts? Right? I won't be able to do this in polynomial time. So that's what we need to overcome. We need to deal with an exponential number of terms in the cut formula. Any other questions at this point? Okay. So the main idea in this work by Karger that deals with this issue is the following. It says that when a reliable network fails, and by reliable network, I mean a network that does not really fail very often, right? The probability of failure is small. Probability of disconnection is small. So when a reliable network fails, it almost always does so because of a small cut. So I'm not going to prove this, but it's intuitively clear what's going on. So a graph has a lot of different cuts. Small cuts are more likely to fail than large cuts. Every edge is failing with probability p. So small cuts in general are more likely to fail than large cuts. However, there are few small cuts. There are many large cuts in a graph. So this says that if the overall failure probability is small enough, then the gap between small and large cuts failing becomes large enough that large cuts become unlikely to fail. It's really a small cut that will cause your graph to disconnect. Okay, that's sort of morally what this statement is saying. And if you're like in terms of precise numbers, it says that when the reliability is less than, unreliability is less than something like n to the minus 4, some polynomial, inverse polynomial, then the probability that a cut of value greater than twice the minimum cut failing is really tiny compared to the overall unreliability. So I can basically ignore this event. This event is going to be absorbed in my approximation. So as long as unreliability is smaller than 1 over n to the 4, I can ignore everything except the edges of size at most twice the minimum cut of the graph. Okay, so that means that what I can do is I can take my cut formula. It has an exponential number of terms, but I truncate the cut formula at only the cuts of value at most 2 times the minimum cut. All the other cuts are completely irrelevant, like are capped, like the approximation deals with that. Yes, I can throw away all the other cuts, just focus on the cuts that are small. These are the ones which will almost always fail if the graph needs to fail. Okay, and then there is this very standard and well-known lemma due to Karger that says that how many cuts do I have whose size is at most 2 times lambda? It's only n to the 4 cuts. Okay, in general, if I have any multiplier alpha, then the number of cuts of value at most alpha times lambda is at most n raised to 2 alpha. So that says that I can take my cut formula, truncate it to the first n to the 4 terms if I'm ordering the cuts by size, truncate it, and then now I have a polynomial size formula. On this, just apply the Karpluby-Madras algorithm, and you'll have a reliability algorithm. Now the problem of the catch, of course, is that I have this condition that the unreliability is smaller than n to the minus 4. So what if it's larger? Okay, if the unreliability is actually larger than n to the minus 4, then the entire thesis doesn't work, right? Because the basic assumption that the graph always fails at a small cut is no longer true. However, this is actually a very easy case, as Michael sort of alluded to a little earlier. So here you can just do Monte Carlo sampling. If the graph getting disconnected is not an elusive event, it's something you can actually observe in polynomial time, then of course we know how to deal with such events, how to count such events. So all you do is you just create a bunch of samples. So you just run the process of failing edges. That creates a sample of g of p. On that sample, you define this the indicator of whether the graph has gotten disconnected, and that's your estimator. Repeat this a bunch of times. It's an unbiased estimator. If you repeat this about 1 over the unreliability times, then that will give you a good estimation. Okay, I mean, this is just standard statistics. There's nothing special. Okay, so that's the entire algorithm. Any questions about this algorithm before we go to sort of the second generation? Yes.
The part about having all the cuts listed in order, is that difficult?
No, that's not difficult. It's easy to, you can use essentially any modification of a minimum cut algorithm to enumerate all cuts. That's at most twice the minimum cut. For example, the contraction algorithm that you might have seen. Any other questions? Okay. So that's, as I said, that's about the first generation of algorithms, and that brings us to the second generation. So the second generation of algorithms for unreliability, the first example of that was this algorithm by Karger in 2016. So it gets exactly the same sort of guarantees as the previous algorithms, except that it's faster. It's not faster by a lot. So remember, the Harrison Srinivasan algorithm ran in time about n cubed times some subpolynomial term. So this new algorithm is replacing that subpolynomial term by some polylogarithmic terms. So it's a slight improvement, but conceptually it's a big leap, and we'll see what new ideas it brings in. And because it was conceptually a big leap, Karger went on in a couple of results to refine the running time. Initially from n cubed, it went down to n to the 2.78, and then all the way to n squared. So I want to mention that these, in the first step, going from n cubed to n to the 2.78, the algorithm changed. So it's the algorithm, in fact, the one that I'll talk to you about, the one I'll present to you, is the one that was given in 2017, the one that gets n to the 2.78. In the second step, going down from 2.78 to 2, that's exactly the same algorithm, it's just a better analysis. Okay. But in any case, all of these three use the same basic idea. It uses it in a more refined way in the later algorithms, but the basic idea is exactly the same, and is quite different from what was happening in the previous generation. So what is this basic idea? So if you remember, one of the basic tools we have for a problem like this is Monte Carlo sampling. I want to generate samples of this graph g of p. Okay, this is a random graph. I want to generate samples of this graph. How do I generate a sample of g of p? Now, the naive thing to do would be to say that I'll take every edge, I'll toss a coin on the edge. With probability p, the edge goes away. With probability 1 minus p, it stays, and that gives me a sample. But let's look at this process slightly differently. So let's assign an independent random variable r sub e to every edge e. Okay. So I just toss a coin on every edge, assign an independent random variable. Now, of course, it's the process that I outlined is equivalent to saying that if the value of r sub e is smaller than p, the edge should be deleted. If it's larger than p, it should remain. But now, instead of deleting any edge, let me do something else. Let me take all the edges whose value is larger than p, so r sub e is larger than p, and let me contract those edges. Okay. So earlier I was taking the edges whose value is less than p, deleting them, and trying to figure out if the graph stays connected, if there's a single connected component. Now I'm looking at the edges that are preserved, the ones that have value larger than p, I'm contracting them. And now my test is does the graph collapse into a single vertex? Right? If there's a single connected component and the edges are contracted, the graph will collapse into a single vertex. So it's completely equivalent to say that I'll contract edges with r sub e greater than p and check if the graph is a single vertex. Okay, so here's an example. So I have these edges. I'm drawing the edges as balls, the random variables corresponding to the edges as balls. And then there is this threshold p. Everything below this was being deleted. Now I'm contracting everything above this. And of course, my main challenge is that the variance of this estimator is very high when p is small. It's just a Monte Carlo estimator. So the variance will be very high when p is small. So let me go in and artificially reduce the variance. How do I do that? So instead of just having this one threshold p, let me create an artificial second threshold q. Now, edges that are above this, all the balls that lie in this zone, these edges I can safely contract, because even with the threshold p, they would be above the threshold. So those are edges that I can contract. Edges that lie in this box, I really don't know what's going on with them yet. Okay. So what I do is I set this threshold q that's deliberately chosen to be a larger threshold and contract all the edges that appear above q. That generates a random graph for me. Okay. So how do I choose this q? I choose this q basically morally in a way that my variance remains small, okay, of the process. And it turns out that the right thing to do is to choose q roughly such that the value of unreliability with q is about 1 over n squared. Let's just think of it as some polynomial. Right? I'm forcing myself to choose a queue such that the event of graph disconnecting has polynomial probability. So it's a low variance event. It's the kind of variance I can deal with. And I've gotten this graph H now. Okay, so I've contracted the blue edge. So E3 has disappeared. I've contracted those, and E1 and E4 are still there. So I have this random graph. Any guesses as to what I should be doing on this graph now in order to obtain an estimator for the original problem? Sorry? Recurse. And that's exactly what we do. So we just take this graph and recurse with the conditional probability P over Q in this smaller graph. Now, what's the advantage? Like at first glance, it seems like, well, I mean, what am I really gaining by doing it in 2 steps rather than doing it directly? The advantage, and of course, I recurse and then I have to repeat a bunch of times, take averages, but that's just to kill the variance. Okay, but that's just standard. The advantage is that H is much smaller than G. So this recursion, the recursive call is much more efficient. So if you look at this graph, for instance, the one that the example I've drawn, what happened is that when E3 got contracted, the edge E2 just vanished, and I don't even need to care about what's going on in that edge. And of course, this is a very small graph. In general, the graph will get contracted into a much smaller graph. And on this smaller graph, I can run my recursion much more efficiently. So does this remind anyone of an algorithm that you have seen for, let's say, for minimum cut? Karger-Stein, exactly. So this is exactly the same idea as in the recursive contraction algorithm of Karger-Stein. Right? Just being applied to a different problem here, but basically the same idea if you have seen that algorithm. Any questions about this process? Okay, and basically, if you do this the correct way, do the analysis correctly, then you can show that this whole thing can be run in the same time as Karger-Stein, if you're familiar with it, in n² time in general. All right, so that's what you get when you introduce this new idea, the recursive contraction idea, into this problem. You get down to n². But now you hit what is sort of a basic barrier. And I'm calling that the quadratic barrier. Okay, so what's this barrier? So it's clear that the estimation of unreliability of U is conceptually related to counting the number of minimum cuts of the graph. So remember, the basic idea in the first generation of algorithms was to truncate the cut formula at the small cuts. In particular, wherever you truncate, it must include all your minimum cuts. That's the smallest value you have. So it seems like conceptually you really need to be able to count minimum cuts in order to be able to estimate U in any reasonable approximation. So counting of minimum cuts is hidden inside this problem in a very deep conceptual manner. Now, how are these algorithms counting minimum cuts? So in principle, both the first and second generation of algorithms, they count minimum cuts by enumeration. In the first generation, it's completely explicit. It says that take all these small cuts, and I'll actually write out a formula where I enumerate all these cuts. So it's an explicit enumeration of the minimum cuts. Second generation doesn't use explicit enumeration. It's a recursive algorithm. But if you are familiar with the Karger-Stein recursive contraction algorithm, that can be used to enumerate all the minimum cuts as well. So explicitly or implicitly, both of these algorithms are counting cuts, small cuts, by enumeration. It's going through the list of cuts, and that's how it ends up counting them. Now that has a fundamental issue, because a graph can have n² minimum cuts. So if you're actually counting via enumeration, then in a graph like a cycle where that has n² min cuts, you are stuck. You can't go beyond n² time. So that's a fundamental bottleneck that these algorithms that are counting by enumeration will face. Okay, so you need something new in order to get past this quadratic bound. Okay, and that's what's called the quadratic barrier. Okay, so that now leads me to talk about the third generation of algorithms and our new result. So this breaks through the quadratic barrier, and it's exactly the same trade-offs, except that we now have a running time that's n to the 3 halves. Okay, so we are no longer bound by the n squared barrier. Questions again about the statement of the result? Okay, so let's see what's going on. So as you can imagine, the new contribution that we have is a new estimator for unreliability. Of course, all of these algorithms eventually are outputting estimators, but we need a new type of an estimator now, something that's weaker than being able to enumerate min cuts. So the first theorem that we show is that if your graph is not very reliable, so if the value of u is relatively high, let's say larger than n to the negative 3, then the previous techniques are going to actually are already very efficient. So you can use some combination of recursive contraction and Monte Carlo sampling to get a runtime that's the kind of desired runtime that we want. Okay, so I'm not even going to be talking about how to show this theorem. It needs some technical work, but the basic message is really we should be focusing on the case where the network is very, very reliable, right? So UGP is less than n to the negative 3. And fundamentally, in that case, we show that recursive contraction and, of course, Monte Carlo sampling, both of these run in at least n squared time. Like it's not just a matter of the analysis not being sharp enough. There are graphs where it doesn't do any better. So we need something else.
Sorry, are you saying there's like a phase transition in the running time at exactly this number?
No. So yeah. So for certain graphs, depends on what the graph is. But if you give me a graph that like a specific you can construct specific types of graphs where when u becomes smaller than n to the minus 3, I don't think there's a phase, like it's not a phase transition. Our best analysis at the moment stops at n to the negative 3. This negative result might need a smaller value of u depending on what the graph is. But there is a value of u and a value and a particular graph where if you run the previous algorithms, they will actually take n squared time. Yeah.
Is there an extension of this theorem? Basically, is there anything special about n to the minus 3, or is it more that if there's a lower bound of, say, lambda on the probability of failure, then you can run in m plus root 1 over lambda time?
So the current analysis so these n to the 3 halves and n to the minus, like the threshold n to the negative 3 and this running time n to the 3 halves, these are functions of the analysis that we have.
So in particular, the first analysis could go down a bit.
Possibly, but it can't go down any. But what it won't be able to show is that these techniques get you better than n squared time no matter what u is. So the second thing is saying that that's not possible. There's I can give you a value of u and I can give you a graph where these algorithms must take more than n squared time.
So is the n to the 3 half related to the n cube in the
It is, yes.
It is.
It is related. But those values are functions of our analysis. Right? This n squared lower bound is not a function of anything we are doing. It's just something about the previous algorithms being fundamentally stuck. Yeah.
Sort of building on that, if you're looking at like u bigger than n to the minus 2 instead or something, would the running time be better than n to the 3 halves? Or?
It could be, in principle, yes. It could be, yes. Other questions? Okay. So our new contribution then is to design a new estimator in this range when the unreliability is smaller than n to the negative 3. Okay, so what do we do here? So the first observation is something that was already there, something we have seen already in the previous algorithms. And this says that if you have a very reliable graph, if your unreliability value is small, then you can discard cuts that are large. In particular, for this particular threshold n to the -3, it turns out that we can discard cuts that are larger than 4 times lambda. Okay, so that's something that we have seen already. Now here's one interesting thing that's happening now. So what were we doing in the first generation of algorithms? We were creating this DNF formula. Why did you need to create a DNF formula? Because there's some inclusion-exclusion principle going on in the background, right? So I have these cuts. Each cut fails with a certain probability. That's easy to calculate. But then the cuts overlap. So their failure is not independent. And therefore, I need to write this like complicated DNF formula that captures the inclusion-exclusion phenomenon happening across the cuts. But notice that we are in very reliable networks. So already one cut failing is a very unlikely event. 2 cuts failing is an even more unlikely event. So it turns out that if you are in this range where u is less than n to the -3, you don't need to do all this fancy inclusion-exclusion. You can replace the inclusion-exclusion by simply a union bound over the cuts. So this will lose some information. It will lose information about multiple cuts failing simultaneously, but that's a little o of u event, probability event. I don't care about the small probabilities. I'll absorb that in the approximation. So that makes my life a lot simpler. Right now, instead of writing this complicated inclusion-exclusion based through a DNF formula, what I can simply do is I can take all my cuts. For every cut, let's say cut C1, it's of size, whatever its size is. I write a term that's p raised to that size, and then sum up over all the cuts. Moreover, as I said, I can discard all cuts larger than 4 times the min cut. So in this sum, I get rid of most of the terms. I only keep the terms going from the min cuts to 4 times the min cuts. And that's a new parameter z that I claimed through these 2 observations approximates u up to some little of one term. Okay. So all I care about is estimating z. I don't care about u anymore. Questions about this? Okay, so I want to estimate z. How do I go about doing this? So one thing to note is that although I have done all this truncation and simplification, the number of cuts I'm dealing with is still quite large. Right? So I'm dealing with cuts that are of size 4 times the minimum cut. So the number of such cuts can be something like n to the 8. So really, I have no hope of doing anything explicit. I can't actually like take all these cuts and for each cut figure out what this term is, the p to the alpha lambda term is, and sum them up. Any such explicit process is going to be very slow. So there's no hope for any enumeration or explicit algorithms. So I need to do some sampling, right? I need to estimate this parameter via sampling. I need to create an estimator for this. Now for this sampling, what do I want to do? I want to sample cuts of value at most 4 lambda, right? I don't want to sample other cuts that don't contribute to my estimate, to my parameter. So I really want to be sampling these cuts that are whose value is at most 4 times lambda. And I want to use this quantity p raised to the size of the cut as the weight of a sampled cut. Somehow I need to have an efficient sampling technique that can do this. Okay, so that's our next goal. How do I sample a cut of this size? Now what helps us here is this theorem, this really old theorem by Nash, Williams, and Tutt that says the following. So if a graph has a min cut of lambda, so the smallest cut is of value lambda, then of course it's clear that the number of edge disjoint spanning trees that I can construct in this graph cannot exceed lambda, right? Because whatever is the minimum cut, it has to contribute at least one edge to each of these spanning trees. So the number of edge disjoint spanning trees cannot exceed lambda. This theorem gives a lower bound on this number. It says that the maximum number of edge disjoint spanning trees is no more than lambda, but also no less than lambda over 2. Okay, you can think of this as some kind of as an approximate duality. So if I had a graph of value lambda, I know of min cut lambda, I know that I can construct a lambda over 2 disjoint spanning trees. So that allows me to design the following important sampling algorithm. So what I do is the following. I construct lambda over 2 edge disjoint spanning trees. Now I should mention that although I am describing it in these terms, we don't explicitly do this. Of course, lambda can be large. I don't have any way of actually explicitly constructing these trees. So we use some implicit methods of sampling from these trees. But in principle, think of constructing these spanning trees. Now, once I've constructed these spanning trees, now think of a cut that I'm trying to sample, a cut of value at most 4 times lambda. How many edges do you expect to see in one of these spanning trees from such a cut? Right? This cut has 4 times lambda edges. There are lambda over 2 spanning trees. These are edge disjoint. So in expectation, you don't expect to see more than 8 edges in any one spanning tree. So if I chose a random spanning tree, the expected number of edges from this cut is no more than 8. So that allows me to think of the following surrogate. So I'm not sampling small cuts anymore, but I want to sample cuts that have at most 8 edges in a random spanning tree in this packing. Of course, this is not the same set of cuts, but there is a one-directional inclusion. Every cut that is small must have a small number of edges in a random spanning tree, at least in expectation. So if I focus on just these cuts, that includes all the cuts that I care about. Okay, it might include a lot of other cuts. Many other cuts might have small number of edges in a spanning tree. Okay, and then if once I sample, I weight the sample by whatever is the appropriate function, like p raised to the subcut size. Okay, so this is the picture. I had all cuts. And then I said, because of my observation, I could only focus on cuts of value at most 4 lambda. So that's a very small set of cuts. Now I am going to this larger set that sits between these two sets. That's all cuts that are 8 respecting a spanning tree. 8 respecting just means that it has less than 8 edges, at most 8 edges. Okay. So this is some sort of surrogate set in the middle of these two things. And I'm sampling into that set. I have no way of sampling into this. I don't know how to do that. Okay. So the first observation is that this sampling algorithm can actually be run very efficiently in polylog time per sample. As I said, there's no hope of actually constructing any spanning trees and so on, but you can do there are tricks to make this run fast. The more sort of conceptually interesting question is, what if the measure of the useful cuts, so this dark blue cuts or the purple cuts, what if that measure is really small compared to this light blue set? It's possible this is a small set inside. Right? So I can sample into this light blue set, but I'll really not hit this set. So it's not very useful for me. So how do I deal with this problem? Now, if this is the case, then there are very few small cuts in the graph. What that means is that if I look at pairs of vertices, different pairs of vertices, most pairs are very well connected. It's a very small number of small cuts. So most pairs are well connected. There are a few pairs that are weakly connected. So in this case, what we do is we go to the well-connected pairs that cannot be separated by a small cut, and just contract them. I don't really care, right? If I have a pair of vertices whose pairwise connectivity, the number of edges that are in any cut separating that particular pair, if that's, let's say, 10 lambda, then really any of those interesting cuts cannot separate that pair. So why don't I just contract that pair and continue? Okay, and we can do this efficiently using something called a Gomery-Hood tree that I don't need to describe here. Okay, so once you put all of these together, then we get this. So in very reliable networks, we show that there is an estimator for this quantity Z, which is a surrogate for U, that can be computed in this time, in time that's about n to the 3 halves. Put that together with the theorem I mentioned earlier. In less reliable networks, previous techniques can already be made to speed up to the same running time. And once you put all that together, you get this result of n to the 3 halves running time. Okay, so let me end with a couple of open questions. The most obvious one that immediately arises is like, where did this n to the 3 halves come from? Is this even natural? It seems like the way that we are doing the analysis and the algorithms that we are using, n to the 3 halves is a real bound for that. So it's not that like some slight modifications will improve it to a linear time, but it's possible that the principle that we introduced in this third sort of generation of algorithms, it's possible that that will eventually lead to a near linear time algorithm. And of course, the field of network reliability algorithms, sort of beyond this one specific problem I told you about, is essentially completely open. And so even, as I said, even this very basic question, I give you a graph, every edge fails with probability half. What's the probability that S and T are connected? Even this basic question, there's nothing wrong. That's all. Thank you.
So a couple of questions. So is it implicit in your results already? I don't think so, but I'm hoping that you can do O tilde of M plus the number of min cuts. Suppose.
No. So the sort of bad examples tend to be ones where there's just one min cut, but then a fairly large number of cuts that's slightly larger than the minimum.
Okay, so O plus M plus the number of min cuts that are within a factor of 2?
Yeah, something like that probably, yes. I would think so, yes.
Okay. And I'm just curious because I guess I haven't followed the literature well enough. How do you do Gomery-Hu in linear time?
Oh, that's a new result that we have.
Okay,
like a separate
great.
result.
Okay.
Yes.
So,
Not near linear, that's almost linear. So
Yeah. Okay.
Other questions?
Is there a hope of some parts of this being deterministic?
That's a good question. I don't know of any deterministic algorithms. Even I think the ones for the special cases are not deterministic, like planar graphs and so on. So, yeah. I mean, I don't think anything rules it out. It's just that I don't know of anything.
At the beginning, you promised to make some remarks on reliability as well.
Good. So thanks for reminding me. So so reliability is a very different problem in the approximation world. And in fact, the first polynomial time approximation scheme came 20 years after the unreliability work. So this is a paper by, I think, Guo and Jerome, and they use MCMC methods. So Markov chain Monte Carlo methods. And there's a whole line of work that's followed on after that initial result of speeding up those techniques, but it goes in a completely different direction.
If there are no more questions, let's thank the speaker again. And now we have a break until